At the end of this video, you should be able to describe air resistance as a form of friction and use coefficients of friction to calculate frictional force. The force of friction. Consider a jug of juice at rest, meaning in equilibrium, on a table, as in figure A shown on the screen here. We know from Newton's first law that the net force acting on the jug is zero. Newton's second law tells us that any additional unbalanced force applied to the jug will cause the jug to accelerate and to remain in motion unless acted upon by another force. But experience tells us that the jug will not move at all if we apply a very small horizontal force. Even when we apply a large enough force to move the jug will stop moving almost as soon as we remove this applied force. Friction opposes the applied force. When the jug is at rest, the only forces acting on it are the forces due to gravity and the normal force exerted by the table. These forces are equal and opposite, so the jug is in equilibrium. When you push the jug with a small horizontal force, F, as is shown in figure B on the screen now, the table exerts an equal force in the opposite direction. As a result, the jug remains in equilibrium and therefore also remains at rest. The resistive force that keeps the jug from moving is called the force of static friction, abbreviated as F sub S. As long as the jug does not move, the force of static friction is always equal to and opposite in direction to the component of the applied force that is parallel to the surface, meaning F sub F is equal to the negative force applied, F sub applied. As the applied force increases, the force of static friction also increases. If the applied force decreases, the force of static friction also decreases. When the applied force is as great as it can be without causing the jug to move, the force of static friction reaches its maximum value, represented as F sub S max. Kinetic friction is less than static friction. When the applied force on the jug exceeds F sub S max, the jug begins to move with an acceleration to the left, as is shown in figure C on the screen here. A frictional force is still acting on the jug as the jug moves, but the force is actually less than F sub S max. The retarding frictional force of an object in motion is called the force of kinetic friction, F sub K. The magnitude of the net force acting on the object is equal to the difference between the applied force and the force of kinetic friction, which is to say F applied minus F sub K. At the microscopic level, frictional forces arise from the complex interactions between contacting surfaces. Most surfaces, even those that seem very smooth to the touch, are actually quite rough at the microscopic level, as is illustrated on the screen here. Notice that the surfaces are in contact at only a few points. When two surfaces are stationary with respect to each other, the surfaces stick together somewhat at those contact points. This adhesion is caused by electrostatic forces between molecules of the two surfaces.
Friction makes it more difficult to move an object across the surface of another object. Surface texture, electrical attraction, and other forces that push objects together all affect the friction experienced by the objects. Even if the surfaces of two objects appear to be smooth, they are rough on a microscopic level. In general, as the roughness of a surface increases, the friction increases, and more force is required to move the object along a surface. Even the surface of fluids, such as water and air, can cause friction. The reason swimming provides such a good workout is that you must exert force to overcome the friction created by water molecules. Electrical attraction also plays a role in friction. Pushing a strong magnet across a refrigerator door requires more force than pushing the same magnet across a wooden table. The greater the attraction pushing the objects together, the more the objects resist movement, and the greater the friction. On the other hand, if the electrical attraction is negative and the objects repel one another, friction can be reduced. Maglev trains take advantage of this phenomenon to give a smooth, nearly frictionless ride. Forces such as gravity can also push objects together. The heavier the object being moved across a flat surface, the greater the friction due to its weight. Similarly, if we push down when moving sandpaper across a piece of wood, we increase the force pushing the surfaces together and consequently increase the friction.
The force of friction is proportional to the normal force. It is easier to push a chair across the floor at a constant speed than to push a heavy desk across the floor at the same speed. Experimental observations show that the magnitude of the force of friction is approximately proportional to the magnitude of the normal force that a surface exerts on an object. Because the desk is heavier than the chair, the desk also experiences a greater normal force and therefore greater friction. Friction can be calculated approximately. Keep in mind that the force of friction is really a macroscopic effect caused by a complex combination of forces at a microscopic level. However, we can approximately calculate the force of friction with certain assumptions. The relationship between normal force and the force of friction is affects friction. For instance, it is easier to slide a light textbook across a desk than it is to slide a heavier textbook. The relationship between the normal force and the force of friction provides a good approximation for the friction between dry, flat surfaces that are at rest or sliding past one another. The force of friction also depends on the composition and qualities of the surfaces in contact. For example, it is easier to push a desk across a tile floor than across a floor covered with carpet. Although the normal force on the desk is the same in both cases, the force of friction between the desk and the carpet is higher than the force of friction between the desk and the tile. The quantity that expresses the dependence of the frictional forces on the particular surfaces in contact is called the coefficient of friction. The coefficient of friction between a waxed snowboard and the snow will affect the acceleration of the snowboarder, shown on the screen here. The coefficient of friction is represented by the symbol mu, the lowercase Greek letter. The coefficient of friction is a ratio of forces. The coefficient of friction is defined as the ratio of the force of friction to the normal force between two surfaces. The coefficient of kinetic friction is the ratio of the force of kinetic friction to the normal force, represented as mu sub k is equal to F sub k divided by sub n. The coefficient of static friction is the ratio of the maximum value of the force of static friction to the normal force, represented as mu sub s is equal to F sub s max divided by F sub n. If the value of mu and the normal force on the object are known, then the magnitude and the force of friction can be calculated directly. The frictional force is equal to the normal force. That is to say, F sub F is equal to F sub n. The table on the screen here shows some experimental values of mu sub s and mu sub k, coefficient of static friction and coefficient of kinetic friction, for different materials. Because kinetic friction is less than or equal to the maximum static friction, the coefficient of kinetic friction is always less than or equal to the coefficient of static friction. Air resistance is a form of friction. Another type of friction, the retarding force produced by air resistance, is important in the analysis of motion. Whenever an object moves through a fluid medium, such as air or water, the fluid provides a resistance to the object's motion. For example, the force of air resistance, F sub r, on a moving car acts in the direction opposite the direction of the car's motion. At low speeds, the magnitude of F sub r is roughly proportional to the car's speed. At higher speeds, F sub r is roughly proportional to the square of the car's speed. When the magnitude of F sub r equals the magnitude of the force moving the car forward, the net force is zero, and the car moves at a constant speed. A similar situation occurs when an object falls through air. As a free-falling body accelerates, its velocity increases. As the velocity increases, the resistance of the air to the object motion also constantly increases. When the upward force of air resistance balances the downward gravitational force, the net force on the object is zero, and the object continues to move downward with a constant maximum speed called the terminal speed. There are 4 fundamental forces. At the microscopic level, friction results from the interactions between the protons and the electrons in atoms and molecules. Magnetic force also results from atomic phenomena. These forces are classified as electromagnetic forces. The electromagnetic force is one of 4 fundamental forces in nature. The other 3 fundamental forces are gravitational force, the strong nuclear force, and the weak nuclear force. All 4 fundamental forces are field forces. The forces are described in greater detail in the chapter called Atomic Physics. The strong and weak nuclear forces have very small ranges, so their effects are not widely observable. The electromagnetic and gravitational forces act over very large ranges. Thus, any force that you can observe at the macroscopic level is either due to gravitational or electromagnetic forces. The strong nuclear force is the strongest of all 4 fundamental forces. Gravity is the weakest. Although the force due to gravity holds the planets, stars, and galaxies together, its effect on subatomic particles is negligible. This explains why electric and magnetic effects can easily overcome gravity. For example, a bar magnet has the ability to lift another magnet off a desk. At this point, you should be able to describe air resistance as a form of friction and use coefficients of friction to calculate frictional force.